In pipeline compression, gas processing, and industrial power generation, the turbine is not just a prime mover. It is the center of a complete rotating equipment system. Today, we will examine the Solar Turbines Titan 130, its design, performance, applications, and realistic replacement options. The Titan 130 is an industrial gas turbine from Solar Turbines, a Caterpillar company. It is widely associated with continuous duty industrial service, where reliability, maintainability, package support, and predictable operation often matter as much as peak rating. Typical Titan 130 applications include natural gas compression, pipeline service, gas processing plants, oil and gas production, mechanical drive duty, and packaged power generation. The same turbine family can support different site objectives, but the packaged and driven equipment define the real duty. In mechanical drive service, the Titan 30 is commonly published at approximately 17.5 megawatts, or about 23,470 horsepower, under reference conditions. For technicians, the important path is turbine output, coupling, and the driven compressor load. For generator set applications, the Titan 130 is commonly listed at approximately 16.53 megawatts electric under ISO or reference conditions. That value is not the same as mechanical drive output because generator losses and package configuration affect the delivered electrical rating. A published generator heat rate around 9,630 BTU per kilowatt hour describes how much fuel energy is required to produce electrical energy. Lower heat rate generally means better efficiency, but always compare values under the same rating assumptions. The Titan 130 mechanical drive configuration uses a two-shaft concept, a gas producer that makes high-energy gas flow, and a separate power turbine that delivers shaft power. This separation helps match turbine output to variable compressor operating requirements. The basic gas turbine process is intake, compression, combustion, turbine expansion, shaft power, and exhaust. Air is compressed, fuel is burned, hot gas expands through turbine stages, and useful power is delivered to the load or generator. In simple cycle mechanical drive duty, the Titan 30 is commonly associated with approximately 36% thermal efficiency. That number is useful for screening, but the site result depends on ambient conditions, inlet and exhaust losses, fuel, degradation, and operating point. Replacement discussions usually begin for practical reasons: aging condition, maintenance cost, emissions requirements, life cycle economics, capacity changes, or plant modifications. But a turbine replacement is never just an engine swap. It is an integrated system decision. A critical warning: similar megawatts do not mean a direct drop in replacement. Titan 130, Nova 16, SGT 400, and LM2500 family equipment must be compared using verified model data, package interfaces, shaft speed controls, emissions, and site rating. The Baker Hughes Nova LT60 is a close nominal power class candidate. Published mechanical drive output is about 17.5 megawatts, or roughly 20,500 horsepower. That makes it comparable in headline rating, but not automatically interchangeable in package or compressor service. On a simple comparison, the Titan 130 is about 17.5 megawatts with approximately 36% mechanical drive efficiency, while the Nova LT16 is about 17.5 megawatts with approximately 37.5%. Treat this as a screening comparison, not a final project result. In power generation, published figures place the Titan 130 generator set around 16.53 megawatts electric and the Nova LT16 around 16.9 megawatts electric. Those values are close, but generator configuration, auxiliaries, controls, and site conditions still decide actual performance. The Siemens Energy SGT400 is a different power class candidate. Published mechanical drive output is up to approximately 14.9 megawatts, with efficiency up to approximately 37.1%. That is below the Titan 130 nominal mechanical drive rating, so application matching is essential. For power generation, the SGT400 is generally in the approximately 13 to 14 megawatt class, depending on version. That is below the Titan 130 generator rating, so engineers must compare installed capacity with the site electrical load profile. The Vernova LM2500 family belongs in the higher power aeroderivative category. Unless a specific LM2500 variant is identified, it is better to describe it by family and application class, rather than assigning one simplified output number. An LM2500 family solution brings a different design and maintenance philosophy. It may offer higher capacity, but it also changes the package, driven compressor match, auxiliaries, maintenance approach, controls, and plant integration requirements. At the first screening level, Nova LT16 is close to the Titan 130 nominal power class. SGT 400 is lower and LM2500 family equipment is higher. But power class is only the first filter. It is not the engineering conclusion. For compressor drive service, shaft power alone is not enough. Engineers must check output speed, allowable speed range, torque, coupling arrangement, gear requirements, and the compressor map. The turbine and compressor must work together across the operating envelope. Two turbines with the same megawatt rating can behave very differently on the same compressor. Power turbine speed range, torque curve, ambient temperature, gas composition, and the required station flow can shift the real operating margin. Published ratings are usually based on ISO or reference conditions. Actual site rating changes with temperature, elevation, humidity, inlet pressure loss, exhaust pressure loss, fuel composition degradation, and operating restrictions. Site derating must be calculated, not guessed. Package integration can become the largest practical constraint. Foundation loads, footprint, inlet and exhaust systems, fuel supply, lube oil, electrical interfaces, ventilation, fire and gas systems, and maintenance access can all affect feasibility. Controls and safety systems also need a full interface review. Turbine control, compressor control, plant DCS, emergency shutdown, vibration monitoring, fire and gas detection, permissives, trips, and communications must be engineered as one protected system. Fuel and emissions are another major filter. Fuel composition, supply pressure, Wabe index, contaminants, NOx, carbon monoxide, and local permitting requirements can determine whether a candidate turbine is practical for a specific site. Maintenance strategy must be compared over the operating life. Inspection intervals, overhaul approach, engine exchange options, spare parts availability, OEM support, technician familiarity, and downtime windows can change the economics of the selected machine. A serious lifecycle review includes capital cost, fuel cost, maintenance, outage risk, spares, support contracts, remaining plant life, and future capacity needs. The lowest purchase price is not always the lowest cost of ownership. So the final comparison should be framed carefully. Nova LT16 is a close nominal power class candidate. SGT 400 is a lower power candidate. LM2500 family equipment is a higher capacity aeroderivative candidate. None should be treated as a guaranteed direct replacement. The most important takeaway is that the complete integrated system matters: turbine, compressor, package, controls, fuel, auxiliaries, emissions, maintenance, and plant objectives. A replacement study must prove the match across the full operating envelope. In summary, the Solar Turbines Titan 130 is a proven industrial gas turbine in the approximately 17.5 megawatt mechanical drive class. It serves pipeline compression, gas processing, and power generation. Before any replacement decision, understand duty, performance, and integration. If this engineering breakdown was useful, subscribe, like, and share it with your rotating equipment team. More videos are coming on gas turbines, centrifugal compressors, maintenance, and reliability. Leave your questions below, and I will see you in the next technical session.